On January 24th, 1986, a spacecraft moving faster than 17 kilometers every single second swept past a tilted, pale blue-green world and recorded something that should not have existed. Its instruments detected a belt of high-energy electrons trapped around Uranus at intensities so far beyond anything scientists had calculated in advance that the readings were treated for years as a kind of embarrassing outlier, a glitch to be quietly filed away rather than explained. That spacecraft was Voyager 2, and the electrons it found that day would sit unexplained for 39 years, until a team of researchers finally worked out what actually happened during those 5.5 strange hours near Uranus. What they found forces us to rethink not just one flyby from the 1980s, but the entire way we imagine what is possible at the edge of the solar system. To understand why this discovery matters, you have to understand what Voyager 2 actually is, because nothing quite like it existed before, and nothing quite like it has flown since. It launched from Cape Canaveral in August of 1977, just over 2 weeks before its twin, Voyager 1, even though the naming makes it sound like it came second. Both spacecraft were built to take advantage of an alignment of the outer planets that happens roughly once every 175 years, a celestial lineup that let a single spacecraft use the gravity of one giant planet to slingshot toward the next, trimming what would have been a 30-year journey to Neptune down to about 12. NASA's original ambition was even larger, a 4-spacecraft grand tour of the outer solar system, but budget realities in the early 1970s trimmed that dream down to 2 spacecraft with a more modest official mission. Fly by Jupiter and Saturn, gather data, and see what happens. Everything after that was considered a bonus. As it turned out, the bonus became one of the greatest exploration stories in human history. Voyager 2 reached Jupiter in July of 1979, arriving after its twin, but capturing something Voyager 1 had missed on its way through, a shifting, churning atmosphere with a great red spot that had visibly drifted and changed shape and color between the two encounters. It sent back roughly 17,000 new images of the planet, revealed a faint ring system, and confirmed something that would go on to become one of the most important discoveries of the entire mission: active volcanoes on the small moon Io, the first time volcanic eruptions had ever been observed anywhere beyond Earth. Together, the combined imagery from both Voyagers eventually mapped more than 80% of the surfaces of Ganymede and Callisto to a resolution of a few miles, essentially handing scientists their first real atlas of worlds that had previously been little more than points of light. From Jupiter, Voyager 2 used the planet's gravity to bend its path toward Saturn, arriving in August of 1981. There, it photographed the rings in far greater detail than anyone had ever seen, revealing intricate braiding and structure that raised as many questions as it answered, and it studied the planet's moons closely enough to begin building the case that some of them, particularly the icy moon Enceladus, might be geologically active in their own right. But it was at Saturn that Voyager 2's trajectory diverged from its sibling in a way that would define the rest of its career. Voyager 1 was sent on a path that took it close by Saturn's giant moon Titan, a scientifically vital target because of its thick, hazy nitrogen atmosphere, but that trajectory also flung Voyager 1 up and out of the plane of the solar system, ending any chance it had of visiting Uranus or Neptune. Voyager 2, spared that particular detour, was instead threaded through a very narrow gravitational keyhole that kept it on course for 2 more planetary encounters that no spacecraft, before or since, has ever managed to reach. That is worth sitting with for a moment. Every image, every measurement, every discovery we have ever made about Uranus and Neptune from a spacecraft up close, every single one of them came from this one machine, launched in the era of disco and the Cold War, running on computers with less processing power than a modern key fob. Voyager 2 arrived at Uranus on January 24th, 1986, after a 5-year journey from Saturn, and it remains to this day the only spacecraft in history to have visited the 7th planet. It is worth remembering just how strange a world it was flying into. Uranus doesn't spin like the other planets. It rotates almost completely on its side, tipped over by roughly 98 degrees, likely the result of some ancient cataclysmic collision early in the solar system's history. Its magnetic field isn't aligned with its rotational axis the way Earth's roughly is. Instead, it is tilted at nearly 60 degrees and offset from the planet's actual center, giving Uranus one of the strangest, lopsided, corkscrewing magnetic environments of any planet we know. Voyager 2 had only about 5.5 hours of close approach to gather everything it possibly could before the encounter was over, and the planet began to shrink behind it on a trajectory bent once more toward its final planetary target, Neptune. In that brief window, Voyager 2 discovered 10 new moons around Uranus, moons that were given names drawn from Shakespeare and Alexander Pope, rather than the classical mythology used elsewhere in the solar system. Puck, Portia, Juliet, Cressida, Rosalind, Belinda, Desdemona, Cordelia, Ophelia, and Bianca. It found 2 new rings, adding to the thin, dark ring system that had been discovered from Earth only a few years earlier. and it measured the planet's magnetic field and its surrounding radiation environment, the invisible cocoon of charged particles trapped by that magnetic field, similar in principle to Earth's Van Allen belts. It's this measurement, the radiation belt data, that would end up haunting planetary scientists for the next 4 decades. Here's the puzzle, in plain terms. Every planet in our solar system that has a strong enough magnetic field creates radiation belts, donut-shaped regions, where the field lines trap and accelerate charged particles, mostly electrons and protons, whipping them around the planet at tremendous speeds and energies. The strength of these belts generally scales with a few predictable factors. The strength of the planet's magnetic field, the supply of particles available to be trapped, and the processes that can accelerate those particles once they're caught. Based on everything scientists understood about Uranus in 1986 and everything they've refined in the decades since through comparisons with Jupiter, Saturn, and Earth, the electron radiation belt Voyager 2 detected around Uranus was almost absurdly intense. It was far stronger than models predicted. A planet like Uranus, weakly lit by a distant sun, with a comparatively modest magnetic field and a limited supply of source plasma, should have been able to produce or sustain. It was, in the words of the scientists who eventually revisited the data, off the charts. For nearly 40 years, this discrepancy sat there as an open wound in planetary science, a data point nobody could fully explain. Some researchers wondered if the measurement itself was somehow flawed, though the instrumentation was checked and rechecked and appeared to be functioning correctly. Others tried building increasingly elaborate models of the Uranian magnetosphere, hoping some undiscovered internal process might account for the extra energy, but nothing quite closed the gap. The honest, if unsatisfying answer for most of that time was that scientists simply didn't know why Uranus appeared to be holding on to radiation levels it had no business holding on to. And because Voyager 2 remains the only spacecraft ever to visit, there was no way to send a follow-up mission to check. No way to see if the anomaly Voyager 2 caught was a permanent feature of the planet or a fleeting moment frozen accidentally in the data of a single 5-hour flyby. That single detail, the fact that it was a flyby and not an orbit, turns out to be the key that eventually cracked the mystery open. A spacecraft in orbit around a planet gets to watch conditions change over days, weeks, years, building up a long record that lets scientists separate a planet's baseline, average state from unusual temporary spikes. Voyager 2 got none of that luxury at Uranus. It got one pass, one snapshot, 5.5 hours of data, and then it was gone, hurtling onward toward Neptune, never to return. For decades, that snapshot was treated implicitly as though it represented Uranus's normal, steady-state radiation environment. But what if it didn't? What if Voyager 2 simply happened to arrive at exactly the wrong, or perhaps exactly the right, moment, catching the planet in the middle of something unusual rather than catching its ordinary condition at all? That is precisely the question a team of scientists at the Southwest Research Institute decided to revisit, publishing their findings in December of 2025 in the journal Geophysical Research Letters. Led by Dr. Robert Allen, along with colleagues Dr. Sarah Vines and Dr. George Ho, the team took an approach that simply wasn't available to the scientists of 1986. They went back to the original Voyager 2 measurements and compared them directly against decades of far more detailed observations of Earth's own radiation belts, environments we've now been studying up close, continuously, for the better part of a human lifetime. What Allen and his colleagues suspected, and what their reanalysis appears to confirm, is that Voyager 2 didn't happen to catch Uranus in its typical everyday state at all. It caught the planet in the grip of a rare and violent burst of space weather, similar in nature to major geomagnetic storms that occasionally strike Earth. Specifically, the data suggests that a solar wind structure known as a co-rotating interaction region was very likely sweeping through the Uranian system at exactly the moment Voyager 2 flew past. It's worth pausing to unpack what a co-rotating interaction region actually is, because the term sounds abstract, but the physics behind it is fairly intuitive once you picture it. The sun doesn't emit a uniform, steady stream of particles in every direction. Different regions of its surface, particularly coronal holes, send out streams of solar wind at different speeds, some fast, some comparatively slow. Because the sun rotates, these streams of varying speed get flung outward in a spiral pattern, a bit like water spraying from a rotating garden sprinkler. When a fast stream of solar wind catches up to and slams into a slower stream ahead of it, the two compress against each other, creating a dense, turbulent, magnetically tangled region at the boundary. This compressed, high-pressure zone is the co-rotating interaction region. And because the sun keeps rotating and keeps producing these alternating fast and slow streams in roughly the same pattern, these interaction regions tend to sweep past the planets again and again like a slowly rotating sprinkler head, periodically dousing everything in its path. When one of these interaction regions slams into a planet's magnetosphere, it compresses and disturbs the magnetic field, and that disturbance can generate powerful electromagnetic waves inside the radiation belts, what scientists call high-frequency plasma waves. In 1986, when Voyager 2's instruments detected an unusually intense burst of exactly this kind of wave activity at Uranus, the strongest such signal recorded anywhere during the spacecraft's entire mission, the interpretation at the time was fairly straightforward and, as it turns out, fairly wrong. Scientists believed these waves would do only one thing: scatter energetic electrons out of the radiation belt, knocking them off their trapped orbits and sending them raining down into the planet's atmosphere, where they would simply be lost. Under that interpretation, the waves should have been depleting the radiation belt, not intensifying it, which only deepened the confusion around why Voyager 2 was recording such extreme electron energies in the first place. The missing piece turned out to be something planetary scientists have only really nailed down by studying Earth's own radiation belts up close over the last couple of decades, largely thanks to missions like NASA's Van Allen probes. Those same high-frequency waves that can scatter electrons out of a radiation belt can, under a different set of conditions, do the exact opposite. They can accelerate electrons, pumping additional energy into them and effectively supercharging the radiation belt rather than draining it. Which of these two outcomes wins out, loss or gain, depends on the fine details of the wave properties, the local plasma density, and the geometry of the interaction, details that are notoriously difficult to pin down. But scientists now have a real, observed example of this acceleration process happening at Earth. In 2019, our planet experienced exactly this kind of event, a solar wind-driven disturbance that triggered intense wave activity in the radiation belts and led to a massive acceleration of trapped electrons, dramatically boosting radiation levels for a period of time before things settled back toward normal. That 2019 Earth event is the missing analog that lets the Southwest Research Institute team make sense of Voyager 2's Uranus data. As Dr. Vines put it in describing the research, if a similar wave-driven acceleration mechanism was at work in the Uranian magnetosphere in January of 1986, it would neatly explain why Voyager 2 recorded so much unexpected extra energy in the radiation belt at exactly the moment it flew through. In other words, Uranus almost certainly isn't a planet that permanently, mysteriously defies the normal rules of radiation belt physics. It's a planet that, through nothing but bad or perhaps extraordinarily good timing, happened to get hit by a solar storm at the precise moment humanity's only spacecraft ever sent there was passing through, and we spent the better part of 4 decades treating a temporary storm surge as if it were the planet's permanent baseline. There is something almost poetic about that, and also something a little unsettling. We built our entire scientific understanding of Uranus's radiation environment, everything referenced in textbooks, everything cited in follow-up papers, everything used to plan hypothetical future missions, around a single 5.5-hour glimpse that may have captured the planet in one of its rarest and most extreme states, or rather than anything resembling its ordinary condition. It's a little like trying to describe what a coastal town is like based on a single photograph taken during the worst hurricane in a century. Technically accurate, in the sense that it really happened, but wildly misleading if you assume it represents an average day. Dr. Allen has been candid about how much this reframes the scientific conversation around Uranus. Science, as he put it, has come a long way since that original 1986 flyby, and the ability to take a genuinely comparative approach, lining up the sparse, single-pass Voyager 2 measurements against a rich, multi-decade record of similar events happening right here at Earth, is precisely the kind of analysis that simply wasn't possible for the scientists working with this data in real time back in the 1980s. It took the accumulation of 39 more years of heliophysics, an entirely new generation of spacecraft studying our own planet's radiation belts in exhaustive detail, to finally give researchers the comparative toolkit needed to reinterpret what Voyager 2 actually saw. But solving one mystery, as tends to happen in science, has mostly succeeded in generating several new ones. Confirming that Voyager 2 likely caught Uranus during a rare solar storm doesn't yet explain the deeper physics of exactly how and why these particular waves managed to transfer so much energy so efficiently into a planet's trapped electron population, whether at Uranus, at Earth, or anywhere else. Researchers still need to work out the precise sequence of events, the exact conditions under which these high-frequency waves flip from stripping energy away from electrons to injecting energy into them, and how those conditions might differ at a planet as strange and lopsided as Uranus compared to a planet like Earth with its comparatively well-behaved, roughly axis-aligned magnetic field. And that unresolved physics carries implications well beyond Uranus itself. If a planet's magnetic environment, tilted at an odd angle and offset from its rotational and physical center the way Uranus's is, responds to solar storms in ways that are meaningfully different from Earth's more conventional setup, then everything we think we understand about space weather and radiation belts across the solar system, and potentially at exoplanets with unusual magnetic configurations too, may need a second look. Dr. Allen has pointed out that these findings carry real significance for Neptune as well, a planet with its own tilted, offset magnetic field, and the only other ice giant in our solar system, one that Voyager 2 also visited briefly in the summer of 1989 on the final planetary flyby of its primary mission. It's worth remembering what Voyager 2 actually did once it left Uranus behind, because the Neptune encounter that followed only reinforces how much scientific weight rests on those few brief planetary passes. After Uranus, the spacecraft spent another 3.5 years crossing the gap to Neptune, arriving in August of 1989 for the only close-up visit any spacecraft has ever made to that world either. In roughly the same handful of hours it had spent at Uranus, Voyager 2 discovered 5 new moons, 4 rings, and a vast swirling storm system nicknamed the Great Dark Spot, an atmospheric feature roughly the size of Earth that, strangely, had vanished entirely by the time the Hubble Space Telescope looked for it again just a few years later, replaced by different dark storms elsewhere in the atmosphere. It also gave scientists their first real look at Neptune's largest moon, Triton, an icy world with active geysers venting nitrogen gas, and dark streaks of material across its surface, orbiting backward relative to Neptune's rotation. A strong hint that Triton was likely captured from the Kuiper Belt rather than forming alongside its planet. Every one of these findings, at both ice giants, came from data gathered during flybys measured in hours, rather than the months or years an orbiter would eventually provide, which is exactly why the newly resolved Uranus radiation belt mystery carries such weight. If a single brief pass could catch Uranus in the middle of an unusual solar storm and leave scientists confused for 39 years, it raises a fair question about how many other features recorded during those brief hours at both ice giants, at Neptune's dark spot, at Triton's geysers, might likewise represent temporary unusual moments rather than each planet's steady, ordinary state, information we still have no way to check without going back. That uncertainty is precisely what makes the case for a dedicated future mission so compelling to the scientists working on this problem today. It isn't only about resolving old anomalies out of historical curiosity, either. Uranus and Neptune are the only examples of ice giants in our own solar system. But exoplanet surveys have found that this general size and category of world, larger than Earth, but smaller than Jupiter or Saturn, may actually be one of the most common types of planet across the galaxy. Every additional piece of ground truth data we can gather about how an ice giant's tilted offset magnetic field responds to solar wind, how its radiation belts behave under ordinary versus stormy conditions, and how efficiently it can trap and accelerate charged particles, feeds directly into how astronomers interpret potential habitability, radiation exposure, and atmospheric conditions. On countless planets, we will likely never visit directly, orbiting distant stars far outside our own solar system. All of which builds toward the argument that Alan and his colleagues, along with much of the broader planetary science community, have been making with increasing urgency for years now. It is long past time to send another spacecraft to Uranus. NASA's own Planetary Science Decadal survey identified a dedicated Uranus orbiter and probe mission as its top priority for a large-scale flagship mission in the current decade, a recognition that our understanding of the ice giants has been frozen quite literally in the state Voyager 2 left it nearly 40 years ago. An orbiter, unlike a flyby, would be able to watch Uranus's radiation belts and its bizarre, tumbling magnetic field over months and years rather than hours, distinguishing ordinary conditions from extraordinary storms the way scientists have now learned to do at Earth. It could catch multiple co-rotating interaction regions sweeping past, watch the radiation belts swell and settle, and finally build the kind of long-term data set that would let researchers test directly whether the solar storm explanation for the 1986 anomaly really does hold up, rather than relying on comparison and inference the way the current study necessarily had to. It's a reminder of something that gets easy to forget when we talk about a mission that launched in 1977. Exploration doesn't end when the spacecraft flies past its target and the headlines move on. Voyager 2's encounter with Uranus lasted a matter of hours, but the scientific process of actually understanding what it saw has now stretched across nearly 4 decades and counting, and it isn't finished yet. The data tapes recorded during that brief flyby have outlived entire scientific careers. Researchers, who weren't even born in January of 1986, are now the ones pulling the original measurements back out, running them against tools and comparative data sets nobody in the Reagan-era Jet Propulsion Laboratory could have imagined. And finally, making sense of readings that sat quietly, stubbornly unexplained for the entire intervening span. While all of this analysis of decades-old data was unfolding here on Earth, Voyager 2 itself, the actual spacecraft, has continued its own extraordinary journey, and its current situation is almost as remarkable as anything it recorded back at Uranus. It crossed the heliopause, the boundary where the constant outward pressure of our sun's solar wind finally gives way to the thin, cold material of interstellar space in November of 2018, becoming only the second human-made object in history to leave the bubble of our solar system following its twin, Voyager 1, which had made the same crossing 6 years earlier. Voyager 2 is now well over 12 billion miles from Earth, a distance so vast that a single radio signal traveling at the speed of light takes roughly 19 hours to reach it, and another 19 hours for any reply to make its way back. A simple back-and-forth conversation with the spacecraft, sending a single command and confirming it was received, takes the better part of 2 full days. Both Voyagers are powered by radioisotope thermoelectric generators, devices that convert the heat given off by the natural decay of plutonium-238 into electricity, and that power output has been steadily, predictably declining since the moment each spacecraft left Earth, losing a small percentage of its capacity every year as the radioactive material decays. Engineers at NASA's Jet Propulsion Laboratory have been managing that slow decline with remarkable ingenuity, methodically switching off individual scientific instruments, heaters, and other subsystems, one at a time over the years, specifically to stretch out the mission's lifespan and keep the spacecraft's most essential instruments running for as long as physically possible. It is, in a very real sense, a decades-long exercise in triage, deciding which pieces of a 50-year-old machine deserve the increasingly scarce electricity it still has left to give. Communication with the Voyagers isn't just a matter of vast distance and light speed delay either. It also depends entirely on Earth's deep space network, the global array of enormous radio dish antennas positioned around the planet, specifically to maintain contact with spacecraft this far from home. Even small errors introduce real complications. In the summer of 2023, an incorrectly formatted command sent to Voyager 2 caused its antenna to tilt just 2 degrees off its intended alignment with Earth, a seemingly tiny error that was nonetheless enough to break the communication link entirely, because across a distance of more than 12 billion miles, even a 2-degree offset translates into the antenna's narrow radio beam missing our planet by an enormous margin. Mission engineers spent weeks working out how to recapture the signal, ultimately succeeding through what amounted to an interplanetary shout, a colossal burst of transmission power aimed at the spacecraft's last known position. And Voyager 2 responded, correcting its orientation and reestablishing contact just as engineers feared they might have to wait months for its onboard software to automatically reset itself and point back toward home on its own. Despite everything working against it, the sheer distance, the failing power supply, computer hardware that is now approaching 50 years old and running on a small fraction of the processing capability found in a modern calculator, Voyager 2 keeps going, and it keeps sending back data from a region of space no other operating spacecraft has ever reached. Its remaining instruments continue to measure the magnetic fields, charged particles, and plasma density of true interstellar space, providing scientists with their only direct or real-time measurements of the environment that exists beyond the influence of our own star, a region theorists had speculated about for generations, but that no instrument had ever actually sampled until the Voyagers arrived there. And, of course, both spacecraft still carry their most symbolically resonant piece of cargo, the Golden Record, a gold-plated copper phonograph disc affixed to each spacecraft's exterior, etched with sounds and images meant to represent life and culture on Earth. Greetings recorded in 55 different languages, music ranging from Bach and Beethoven to Chuck Berry, the sounds of wind, thunder, and whale song, along with more than 100 photographs depicting our planet, our biology, and our civilization. It was assembled by a committee chaired by the astronomer Carl Sagan, under the assumption, however remote, that someday, perhaps tens of thousands or even millions of years from now, some other intelligence might encounter one of these spacecraft, drifting silently through the galaxy and wonder who sent it. Voyager 2 will keep carrying that record long after its instruments finally go silent and its power runs out for good, something engineers currently estimate could happen sometime in the early 2030s, if the careful instrument-by-instrument power management continues on its current trajectory. Even after that happens, even after the last signal ever received from Voyager 2 has been logged and archived, the spacecraft itself will continue drifting outward, silently, for essentially the rest of time, carrying its golden record through the emptiness long after every person who worked on the mission, and quite possibly every trace of the civilization the record was built to represent, is gone. That's the strange, layered nature of what makes this newly solved radiation belt mystery so compelling. It isn't a story about a spacecraft actively out there right now making some new, live discovery in real time, the way headlines sometimes imply. Voyager 2 finished its work at Uranus back in January of 1986, decades before most of the researchers now studying that data had even been born. What's new, what's genuinely remarkable, is that scientists in 2025 were able to reach back across nearly 40 years, pull out measurements gathered during a 5.5-hour window that has been sitting in mission archives since the Cold War, and finally figure out what those measurements were actually telling us by comparing them against a completely different planet, our own, studied so much more closely and for so much longer than Uranus ever has been. It's a reminder that a single flyby, however brief, can generate a scientific legacy that keeps producing new insights for generations, as new tools, new comparative data sets, and new generations of researchers return to data that was once considered fully analyzed and finished.